In this part of the lecture, we will implement the object-oriented design that we achieved in the last part, in part 1 of the case study. We were able to recognize the classes that we will be creating, and we were able to add the fields and the methods of those classes, as well as the relationships between the classes in our object-oriented design. As I have mentioned earlier, that this case study is part of an older version of the book, an older edition of the book, the Deitel and Deitel 8th edition. If you are interested in reading the book, and these slides are solely the property of Pearson Education. And in this part, we will be looking at how to convert our class diagrams to Java code. And then we will gradually tune our code by incorporating the concepts of inheritance and polymorphism. And finally, we will be achieving the full Java code of our ATM software. Now, we are advised to try and implement the code by your own. Otherwise, the code will be provided for this case study. This case study is a kind of a blueprint that you can follow for any of your projects or any of your assignments that you are provided or you will be provided, from starting from the analysis stage, the design stage, and going on towards the implementation of your software. This was the class diagram that we achieved without the relationships. So we have our classes and their variables and methods. Navigability shows us the flow of our or the relationships of our classes. The class diagram in figure 13.2 further refines the relationships among classes in the ATM system by adding navigability arrows to the association lines. Programmers use navigability arrows to determine which objects need references to other objects. And this is one of the important things that to identify earlier in our development, that which programs or which classes will include references to which of the other classes in the system. Associations that have navigability arrows at both ends or have none at all indicate bidirectional navigability. That means both of the classes are interrelated to each other. Navigation can proceed in either direction across the association. So this is the diagram with the navigability arrows. You can see that the ATM will have a reference to the deposit slot or an object of the deposit slot, an object of the keypad class, an object of the cash dispenser class, and an object of the screen class. Similarly, it will have an object of the withdrawal class, possibly of the database class, and the database class will have an object of the account class, and the withdrawal class may have a reference to the bank database. So these arrows show us the kind of references that we'll need from one class into another class. Implementing the ATM system from its UML design, we are now ready to begin implementing the ATM system. Convert the classes in the diagrams of what the figures 13.1 or 13.2 into Java code. So in this our next stage, we will be converting our diagrams into the Java code. The code will represent the skeleton of the system. So initially we will create our classes and add the code that we can initially, and then make further amendments and additions to our initial code. 4 guidelines for each class. Use the name located in the first compartment to declare the class as public class with an empty no argument constructor. And that is how we have been creating our classes. We start with the name of the class, and the name of the class have been identified by the top compartment in our class diagram. So we start creating our class with the public class and with a constructor that is initially a no argument constructor. Use the attributes located in the second compartment to declare the instance variables. Use the associations described in the class diagrams to declare the references to other objects. Use the operations located in the third compartment to declare the shells of the methods. So if we have not yet specified a return type for an operation, we declare the method with return type void. Refers to the class diagrams to declare any necessary parameters. We have identified all of our classes, the names of our classes, the attributes, the associations between those classes, our methods. There may be return types. If not, then we can initially have a void as return type, and we can add the necessary parameters if we already have declared them or we have recognized them. So this is an initial structure of our public class, our class withdrawal with the no argument constructor. This can be as initial shape of the class. Then in the next stage we add our instance variables to the class, followed by the reference to the other classes that this class might have. So this class will need to have a reference to the ATM screen, the keypad of the ATM, the cash dispenser, since when we are withdrawing cash from the ATM machine, we need access to the cash dispenser of the ATM machine, and then of course it will have a reference to the bank database. Now these were the relationships that we have identified in our class diagram, and this shows us the usefulness of using class diagrams and the process of designing, that we instantly know which variables and which methods that we can add to our classes. We might need to add more details to our class, or we might need to remove some of these details, but it has given us an initial structure of our class. Now we can add a method like the public void execute method to our class. Incorporating inheritance and polymorphism into the ATM system. Now if we study our class diagram in a little more detail, we can apply inheritance. Maybe if you look for commonality among classes in the system, create an inheritance hierarchy to model similar yet not identical classes in a more elegant and efficient manner. So we can combine the common details of the classes. Of course they won't be identical, since we do not need to create identical classes, but they will be similar in most of the cases, situations or cases, or their details. Modify class diagram to incorporate the new inheritance relationships. Translate updated design into Java code. So we will modify our class diagram based on the new analysis, and then of course update our Java code as well. By looking at the diagram, we can identify that these three classes have some common details. For example, the account number is common among all of these classes, the amount is common among all of these classes, and the execute method is common among all of these classes. So we can maybe try to have a super class for all of these classes and then add them as part of their super class to the class diagram. The super class can be identified with the name transaction, and the common details from all of these classes have been added to the super class. The common methods and the common instance variables, while the details specific to each of these classes have been left within those classes. Class diagram modeling generalization of superclass transaction and subclasses balance inquiry, withdrawal, and deposit. Note that abstract class names, transaction, and method names execute in class transaction appear in italics. So the class name is the transaction class is abstract, and we can depict an abstract class or an abstract method in our class diagram by writing them in italics, as we can see in this diagram. If you remember the details of abstract classes, the abstract classes cannot be complete without their subclasses. So a transaction can only be a balance inquiry, a withdrawal, and a deposit. It cannot be anything other than these three transactions in our system. And that is the advantage of making the superclass as abstract, that it cannot, for example, we do not want our transaction to be any other of anything other than these three types of transactions. Therefore, we can make our class as abstract. Polymorphism provides the ATM with an elegant way to execute all transactions in the general. The polymorphic approach also makes the system easily extensible. To create a new transaction type, just create an additional transaction subclass that overrides the execute method with the version of the method appropriate for executing the new transaction type. So we can incorporate polymorphism into the system, and now we have this new diagram or class diagram of our ATM system. With this additional detail that we have a superclass transaction and all of the classes are now interacting with the superclasses, and then there are some interactions between the subclasses and the other classes as well. And again, we always show the name of the abstract class in italics, so it's a bit different from the other classes, that it shows that it is an abstract class. Now we have added another class to our class diagram with some of the features, and one of the features is that it is an abstract class and it has an abstract method. An abstract method compels all of the subclasses to implement that method. So all of the subclasses of the transaction class will have an execute method. And the code will change as well. Public class withdrawal extends transaction, and then we have the attributes, the constructor, and the execute method that is now overridden from the superclass. Consider the classes in the order in which we identified them in section 12.3 in our part 1 of this lecture. These were the classes that we identified. Apply the guidelines discussed in our previous section to code these classes based on how we model the UML class diagrams of figure 13.9 and 13.10. So we need to implement all of these classes one by one with the details that we have identified already, and we may need to add more details to them, but we will have an initial structure or skeleton of all of our classes of the ATM case study. Our ATM design does not specify all the program logic and may not specify all the attributes and operations required to complete the ATM implementation. This is a normal part of the object-oriented design process. Now, any design is supposed to provide you an initial structure that you can follow to develop your system. There might be details that you might need to add after you have started implementation, after testing, or after evaluating your system in detail. As we implement the system, we complete the program logic and add attributes and behaviors as necessary to construct the ATM system specified by the requirements document in section 12.2 in our previous part of this lecture. So looking at our requirements documents in our design, we can look at our we can declare our class ATM. Now the ATM class will have a boolean variable for authentication of the user. As we can see, the current account number, the user's account number, that is the user that is using the ATM machine. The ATM will have an object of the screen class. Since an ATM is supposed to have a screen, it is supposed to have a keypad, it is supposed to have a cash dispenser, deposit slot, and it is supposed to have access to the bank database. Similarly, if you remember, we said that we will have a menu, we will offer a menu to the user to choose from, and that menu will have these four options, and we will proceed ahead based on the choice that the user selects from the screen. We have declared them as constants since we do not want these variables or these options to be changed during the runtime of the program. So a 1 should always be used for balance inquiry, a withdrawal, a 2 should always be used for withdrawal, a 3 should always be used for deposit, and a 4 should always be used for exiting the system. And to make sure these do not change, we make these variables as constants, as we can see, and we make them as by using the final keyword, and we also make them static. The constructor of the ATM class, it initializes these variables. So by default, a user is not authenticated, and then we have the objects of the other classes. The current account is 0 by default, and this is the method that will be called, the execution of our ATM system will start. The run method has been declared, and we will call this method from our main method to start our ATM machine. And this method specifically, it displays a welcome message on the screen, and it tries to check if the user is authenticated. It calls an authenticate user method that has been declared elsewhere. Once the user is authenticated, we will perform transactions. This is another method that has been declared elsewhere. And once the execution of this method is complete, we reset the authentication of the user to false, since the user is supposed to have exited the system, and we need to restart the system to a default value. And all of the default values are reset to the system, displaying a message on the screen thanking the user. Now in the authenticate user method, it can be seen that it is a private method, so it can be called a helper method that helps the ATM class to authenticate the user, and the details of this method should stay within the ATM class, and this method should not be accessible from outside of the ATM class. That is why we have made this a private. This will try to access the database and check the details of the user. If these are correct, and then the user will be authenticated. So once the method is called, it sends a message to the screen class to display some message on the screen. It will ask the user to provide some input, as we can see, through the object of the keypad class, and we will store that input in a variable. Then we will ask the user to enter the pin code, and similarly we will store the pin in a local variable. Once we have received these details, we will call the bank databases authenticate user method by providing the details that we have received from the user. Once these details have been verified for this user, we will authenticate the user. And if the user is authenticated, the current number will be updated to the account number we have received from the user. The current account number was initially set to 0, and now it will be set to the account number we have received from the user. Else the screen should display invalid account number or PIN, please try again. Once the user has been authenticated, we can perform transactions. Again, a helper method has been declared for performing transactions. Local variables to store transaction currently being processed. So we have a variable of the transaction class initially initialized to null. The user has not exited the system. While the user is within the system, we can provide the menu to the user. So we display the menu, and we have a switch statement that displays the detail or the menu to the user. These are the options that we can provide to the user, and whatever the choice the user selects from the screen, we will initialize our object to that selection, and we will call the execute method of the transaction type that the user has selected. We had an execute method in all of our subclasses, for example our withdrawal, our deposit, and our balance inquiry classes. And based on the choice of the user, for example the value that the user has selected, that will be passed on to create a transaction, and that value will be initialized to our current transaction. In case the user chooses to terminate the session, we will display a message on the screen, and the user exit should be equal to true. The user did not enter an integer from 1 4, for example. You did not enter a valid selection. So we have all of these options for the user to select from, and in case the user exits the system, we can allow the user to exit from the system without any transaction. Or if the user presses any other digit or any other key from the keyboard, then we can display on the screen that these were the user can only choose from one of the 4 options that we have provided on the screen. Now we have the display menu method within the ATM class. This again is a helper method that will send messages to the screen class to display messages on the screen. Now this is the display menu as we have saw in the previous part of this this program. It displays on the screen view my balance, withdraw cash, deposit funds, and exit the system. The user enters a choice, we get that choice and return that to, for example here where we have called our display menu method, the choice is returned and stored in this variable, and whatever the choice of the user was, for example we check that through the switch statement, and in case it was balance inquiry, the transaction will be initialized to the balance inquiry. If the user chose withdrawal, the current transaction will be initialized to the withdrawal, and if the user selected deposit, the current transaction will be initialized to deposit. And then we can execute the method of the particular transaction that the user has chosen. We will also have a create transaction. They will see As we can see over here, the create transaction is after of the transaction class. This can be called the user defined data type, where we use our class as the data type. Here we are using our class as the return type of the create transaction class. So we have a temporary transaction variable, and based on the choice that the user has entered, we pass that choice to create transaction method. Over here, for example, we pass that choice to the create transaction method. The choice is received here, and in case the user has chosen balance inquiry, our temporary transaction variable is initialized as a variable as an object of the type of the balance inquiry by sending the details that the balance inquiry constructor will require. Similarly, if the user has chosen the cash withdrawal, we initialize our temporary variable to the object of the withdrawal class. If the user we pass all of the details to the withdrawal class, to the constructor of the withdrawal class, and similarly if the user has chosen the deposit, we initialize our temporary variable to the deposit class's object. And that concludes our ATM class. You can look into the code in detail and step by step and try to understand the code and how the code works. Now moving ahead in our program, we will write the code for all of our classes. For example, this is the screen class. It has a method that for displaying any message on the screen. All of the rest of the classes will be passing a message to this method, and this method will be displaying that message on the screen. Similarly, we can have other methods for displaying the messages on the screen with their particular format. So the screen classes will basically display our messages on the screen, and these messages will be activated by the other classes, since we have an object of the screen class in most of our other classes. Similarly, we have a keypad. The function of the keypad is to get an input from the user, and we have been using the scanner class for that purpose. Whenever we have an object of the keypad class, we call the constructor, and the constructor initializes and calls the scanner class, an object of the scanner class that we can use to get the input from the user. The class cash dispenser. The class cash dispenser represents the cash dispenser of the ATM. It will have an initial count that indicates the initial count of pills or the initial number of notes that the cash dispenser has. The class trusts that a client call dispense cash only after establishing that sufficient cash is available by calling insufficient cash. Is sufficient cash available? So obviously whenever we are withdrawing cash from the ATM, it makes sure that it has the cash available, and once the cash is available, we are able to withdraw the cash from the ATM machine. Thus, dispense cash simply simulates dispensing the requested amount without checking whether sufficient cash is available. Obviously, we cannot guarantee that in a simulation, so we just assume that the user is entering the right kind of amount, that the ATM machine has that amount and is able to dispense that cash to the user. To code the cash dispenser class, we have an initial count of the number of nodes that we can have in the ATM machine. We do not want the user to change this value, so we have made this final and static, and we have a variable set count attribute to default. Since we cannot change this initial count variable, we need the count attribute to make sure that we are entering the multiples of, let's say we get an amount from the user that the user wants to withdraw, and we need to calculate the number of notes that we will be dispensing to the user. And in this case they are saying that each note will be a multiple of 20. In our case we can have a note multiple of 500, say, let's say, in rupees, and the count variable is updated. Similarly, the count variable is updated by subtracting the bills that have been drawn by the user, and we try to make sure that we have sufficient cash available. So we have the amount and we have the bills required that we have. If the count is greater than the bills required, return true. If the count is less than the bills required, so if we have more cash in our system than that is required by the user, then we can dispense the cash. Otherwise we cannot dispense the cash to the user. The deposit slot class represents the ATM's deposit slot. The deposit slot has no attributes and only one method is envelope received, which indicates whether a deposit envelope was received. It just checks if an envelope is received and it returns true. The account class, one of the important classes of the ATM system, it has an account number, a PIN code variable, available balance and total balance with the constructor that initializes these values, a method for validating the PIN, and the getter methods for getting the total balance, getting the available balance, method for crediting the amount into the total balance, a method for debiting the amount from the total balance of the user, and of course the get account number method. The bank database class, now as we can see over here, and we have used it previously, that we can create an array of our objects, and in this case, since our bank database is supposed to have multiple accounts, therefore we can have an array of accounts. Initially, for example, we have 2 accounts in our bank database. Since we are not connecting to the database, to a real database, we'll be covering database in our future lectures, but since we have not covered databases, therefore we only simulate that we have an array of accounts and we have hard coded our account details into the elements of that array. We can alternatively get these details from our database, but since we are not using the database, we can hard code these into our elements of the array, the accounts array. So currently our bank database has 2 accounts with these details, the account number and the PIN code and the balance in those accounts, etc. These are the details required by the account class, the constructor of the account class. So we have the account number, the PIN code, the available balance and the total balance of the user. This method, the get account retrieve account object containing specified account number. So it's a helper method, and it will, for example, we have received an account number and it will look for that account number in all of the accounts and retrieve the one that is received by the bank database class. For example, user enters an account number and we want to select that account number from a large list of a large array of our account numbers. So we can look for that account number from within the array by using this for loop, the enhanced for loop. It will try to identify our matching account number, for example. So we go through the array And once we have identified the required account number, we initialize that to our current account number and return that. If no matching account was found, return null. Determine with the user specified account number and PIN match. Now once we have the account number, that account number must match the PIN. So if for example this was account number, then it should match the particular PIN of that account number as well. And this is what we do for trying to make sure that the account number matches the particular PIN of that account number. Attempt to reach the account with the account number. Once we have, if account exists, return result of account method validate PIN. Account number not found, so return false. If the PIN code does not match the account number, we return false. Otherwise, we validate the account number. Of course, it should not be null to be able to find a matching PIN code for that account number. And then we have the other methods, the getter methods and the credit. So everything that is credited into an account should be updated in our database, and everything that is debited from the account should be updated in the bank database this way. So we have all the required methods for the crediting, the debiting, the getting the balance from the database. Most of these methods are similar to the account class, since we need to make sure that each of the transaction or each of the activity that happens to the account class is updated in the bank database. In our transaction class, the class transaction is an abstract superclass that represents the notion of an ATM transaction. It contains the common features of subclasses balance inquiry, withdrawal, and deposit. The class has the three public get methods: get account number, get screen, get bank database. These are inherited by transaction subclasses and used to gain access to class transactions private attributes, as is always the case with the inheritance. So this is our transaction class, and it has the attributes, the constructor, and the getter methods that it needs. You can see that the execute method is abstract, so all of the subclasses of this class must implement this method. The balance inquiry class extends the transaction and represents the balance inquiry ATM transaction. Balance inquiry does not have any attributes of its own, but in inherits transaction attributes, account number, screen, and bank database, which are accessible through transactions public get methods. The balance inquiry class extends the transaction class, and it only needs to show the balance of the user, so it can do that by accessing the public details or the details of the transaction class. For example, it needs to access the account number, the ATM screen, and the bank database, and that is done through the execute method. It must implement the execute method. So the execute method has initializes an object of the bank database, and it has an object of the screen class through the public methods of the transaction class. You can see these methods have been declared in the superclass, and it returns the available method to the user, and that is what this class is supposed to do. And then it calls the screen classes methods to display all of the details on the screen. As you can see that we have different methods for displaying different kinds of detail on the screen. and all of those methods are being used over here. So the first message will display a line on the screen, the second will display this another line, and we will display the dollar amount. We have specific format for this, so that will be displayed and this value will be passed. And similarly, we will again display the dollar amount on the screen for the total balance. The withdrawal class extends transaction and represents a withdrawal ATM transaction. The figure 13.1 models the association between class withdrawal and class keypad and cash dispenser. Cash dispenser forest lines implement reference types attributes keypad and cash dispenser respectively. We will see line 7 and 8 will declare the attributes of these other classes. As we can see that we have the objects of these other classes within the withdrawal class, and the rest of the details, for example, we can initialize through the superclass, and some of the variables, the ATM keypad and the cash dispenser are initialized in the ATM. This class must also implement the execute method, and since we are withdrawing cash from the ATM in this class through this class, initially no cash is dispensed, and we need to have an amount that can be withdrawn. So this is the amount that the user should not exceed. User cannot withdraw more than this amount from his or her account. So we have references to the bank database and the screen class through the super class. So we display the menu of the amounts to the user on the screen unless the user selects cancelled. For example, if the user selects cancelled, we can have another option like cancelled option as well. In the execute method of the withdrawal class, we display the amounts that user can choose from, and we check that amount. We try to make sure that the user has not cancelled the transaction, and once we have the amount, we first make sure that the amount is less than or equal to the available balance of the user. Now where we do get the available balance from, we get the available balance of the user from the bank database by passing the account number of the user. So we can see how all of these classes are interrelated with each other. Now once we have ensured that the amount is less than the available balance of the user, or not, at least not more than the available balance, we try to make sure that we have sufficient cash available in our cash dispenser. If you remember that we had a sufficient cash available method in our cash dispenser class, we call that method to check if the ATM machine has sufficient cash available and that cash is more or equal to the amount that the user is trying to withdraw. Once a true is returned, we debit that amount from the user's account. As we can see over here, we call the debit method of the bank database class and pass the account number of the user and the amount that the user is trying to withdraw, and this amount will be debited from the user's account. The cash dispenser will dispense the cash. Cash dispense is true, so the cash was dispensed to the user, and the message will be displayed on the screen. Your cash has been dispensed. Please take your cash now. And alternatively, if the cash is not available, another message will be displayed on the screen. Similarly, if the amount is insufficient, the message will be displayed on the screen. Or if the user cancels the transaction, the message will be displayed on the screen. And the loop will go on until the cache has been dispensed. When the cache has been dispensed and this variable becomes true, we will exit the loop, and this marks the end of the execute method. The menu amounts are we can display on the screen. The user can choose from one of these options. We can modify this method by using, for example, if you want to make it for rupees, so you can modify this method accordingly. But what it makes sure, what it ensures that the user selects from a menu of banknotes that the user can withdraw. And this is usually the case whenever we use ATM. It asks us to choose from a menu, and that menu is the amount that we can withdraw from the ATM. So the user inputs a choice, and the respective choice will be selected and returned to the calling method. For example, here that will be displayed at this point in our execute method of the withdrawal class. The class deposit extends transaction and represents a deposit transaction, create reference type attributes similar to the withdrawal class, and most of the details are similar to the withdrawal class since these are related through inheritance. And you can go through the details of this. It only makes sure that an envelope has been received, and once the envelope has been received, the user will be asked to enter an amount that the envelope has, and that amount will be credited to the user's account. And that is what it does different from our withdrawal class. And finally, the class ATM case study is a simple class that allows us to start or turn on the ATM and test the implementation of our ATM system. So this will start the ATM machine. It has the main method. This is where our ATM machine will be started from. It will call the run method of the ATM machine. The run method, if you remember, was the ATM class. Now you can go through all of this code in detail and try to implement this from the scratch by following your designs that you have developed and implement that code. The code for this ATM case study will be provided, and you can check the code. You can see how we move from analysis to this design and then implementation in our object oriented programming. This will conclude this lecture 20 for us, and we will see you in the next lecture.